Now we're going to talk about resampling, and this is effectively sampling of sampled signals and what that implies to reconstruction. So first off, why do we even want to consider that? Well, sometimes you have a really large subsystem in which you're transmitting digital information around these digital signals, and those subsystems are designed for different sampling rates. So some of them are really high quality, some of them are really low quality, and you need to switch back and forth between those sampling rates. That requires us to alter the sampling rate of an already discretized signal. So effectively what we are doing is taking the original signal, which was sampled with a sampling period T1, and we want to create another signal which is effectively the original signal sampled at some other period T2. Now, we want to avoid having to do this with going to analog, resampling, and then redigitizing. It's more efficient if we do it all digitally. So what this process is involved is it's either downsampling, where we're reducing the sampling rate, or we're upsampling or increasing the sampling rate. And we're going to take a look at each of those in turn here. So let's talk about downsampling. So what we're doing is we are reducing the sampling by an integer factor d. And effectively what we are doing is, if we start out with a signal x1, if we scale it by 2, then effectively what we're doing is taking every other sample. If we scale it by 3, we're taking every third sample and creating a new signal. So if we take a look at that downsampling by a factor of 3, we're keeping every third sample. So if this was our original signal, then this is our new signal. And remember, this index doesn't really mean anything physically at this point. So this came from the samples of the original sampling period. The spacing is actually 3 times as wide in time now, even though it's not indicated in the graph of n, graph versus n. So for each sample that we retain, there's actually d minus 1 that are discarded. So are we losing any information by doing this? And to be able to think about that, we need to take a look at things in the frequency domain. So let's say we had our original signal x of t, which has a spectrum x of omega. That signal was sampled at some sampling rate fs. And we know that the spectrum of that is that discrete time Fourier transform indicated here, where we just get shifted copies of it. Well, the downsampled signal is effectively taking that original signal, and now what we end up with is a discrete signal which is effectively sampled at a lower sampling rate, fs over d. And so the spectrum of that should just be the same idea as what we had before. It's just those spectral copies are not shifted as much. So if this was our original signal, this was our original sampling rate. If we downsample those that digital signal, then the spectrum of what we end up with will look like that. And notice that the scale of capital omega has not changed, but what has changed is the stretching of the spectrum. That's because, remember, that capital omega is actually normalized already, so it's effectively like we have stretched out the spectrum. Okay, but that can be a problem because although we might have sampled originally at a high enough Nyquist rate, once we downsample, you can see that these portions here might start to overlap, and so we may run into aliasing issues. And so as a solution to that, what we do is we actually filter before we do the downsampling. And this combination of an anti-aliasing filter, and it's digital, an anti-aliasing filter and downsampling, that whole thing is called a decimator. And ideally that anti-aliasing filter would just look like that. So imagine we're taking that spectrum and just filtering out that lowest portion of it. And hopefully that should avoid these problems. Now let's take a look at the reverse, which is upsampling. So this might seem a bit strange. It seems like we're starting with some samples and then we're all of a sudden magically creating extra samples in between. Well, how do we define those extra samples? Well, what we do is we actually take those original samples and then we fill in the spaces in between where we've got extra samples with zeros. And that's a process called zero filling. So zero filling means we are filling in the spaces in between samples with zero. And that's what we do when we do upsampling. Now, is that really adding any useful information? It seems like we're creating information out of thin air, but remember those zeros do not represent the original signal, and we'll have to deal with that. So again, let's take a look at the frequency perspective. So if we have the spectrum of the original signal, if we have the original signal and it has a spectrum, or DTFT x of omega, now take a look at our upsampled signal. Well, if you go through the process of calculating that spectrum, it's really just the original spectrum stretched. It's actually compressed because L is greater than 1. So if this is our original spectrum, now we have a compression of that, and this would be our upsampled spectrum. Now we're not going to run into any aliasing problems here per se, because we started with something with no overlap, so when we compress it, there's not going to be any overlap. But we do have to deal with this problem where these zero samples, they kind of need to blend in better to actually represent that original signal that it came from. So if you think about trying to reconstruct this, what we'll actually want to do is remove those spectra, again, beyond that first or lowest order copy. And so effectively what we're doing is we're doing the upsampling, and that would give us this spectrum. And then what we're going to do is put in another filter to get rid of these chunks on the side. And so we have an ideal interpolation filter which looks like this. And note that it is a sinc function as well, but it's a discrete sinc function. Now the problem is that's not really doable in practice, and so we'll just take a look at the reverse of what we did before, which is we could use a zero order hold interpolation filter, or we could use a first order hold interpolation filter and that's what that is doing is it's effectively filling in the spaces between the zeros, between the samples. So remember we created those extra samples where we just arbitrarily said let's just make them zero, and what that interpolation filter does is it actually smooths out the spaces in between real samples here. Okay, and that's all we're going to have, and we're going to take a look at reconstruction when you do your worksheet.